this section on probability, the first thing I guess I should mention is that there are 3 different approaches to probability mentioned in your book. Okay? And they list them as follows. They list them as relative frequency approach, the classical approach, and the subjective approach. And I guess the names are not important. But the idea that probability is done in different ways is important. And can you guess which approach I am most familiar with? Just by the name? The classical approach. I'm going to emphasize this guy because here is where I feel I can be helpful. I can help you to understand classical probability. Okay? And so I will talk about this today quite a bit. Okay? Let me go backwards, though, and just say, when we do something called subjective probability, okay, what you are doing here is you are estimating using what I'm going to call expertise. Okay? And I am not an expert in just about anything this book has to say. So I will not be doing subjective probability with you. Okay? You will see it in there. You will see it mentioned. There'll be an exercise or two, and they will talk about what it is, but I'm going to stay away from that. Now, I am going to talk about this kind of probability, relative frequency. And see, those words are words you've had before. Because we talked about frequency distribution, and we even talked about relative frequency distribution. All right? And I'd like you to take a moment to talk to someone near you about what do those things mean. That would have been food for today's exam. So let me pause. Okay. Relative frequencies. Any thoughts that you wanted to share with everybody? Yes. Jessica. Right. So we talked about that. A frequency, right? A frequency is the number of times something occurs, but a relative frequency means we're going to get a percent. And how do you get a percent? Yeah. Sure. You take frequency and then divide by the total, right? So when we talk about probability being a relative frequency, I think the important thing to understand right now, and then we'll come back to it, is that we're talking about it being a percent or also a fraction. And so when you said, how do you get the percent? Well, you take something and divide by something else. I think right now that's the first point I want to make. Again, a probability is a percent or a fraction. And when I say it's a percent or a fraction, what's the largest probability you could have? 100%, which is what fraction, by the way? 1 over 1, right? It's 1 as a fraction. And what's the lowest probability you could have? I guess 0%, and that's what we would call impossible, right? And we think of it as a percent or a fraction in both of these approaches, the relative frequency approach and the classical approach. Now, like I said, I want to emphasize classical, so I'm going to start with that. And then we'll come to this. So, some notation right off the bat. If I give you capital P, that means probability. Capital P. We're going to use capital letters A, B, and C for what we call events. Now, what is an event? It's not really necessarily the English usage of the word, but here's the idea of how these things are going to be used. I am going to compute P of A, the probability of event A occurring. Okay? So, for example, I could compute the probability of rolling a 4 when I roll a 6-sided die. Now, do you see how long it took me to write that out? That's kind of annoying. So what I would do, if I was going to be talking about things like this over and over again, is I would say, hey, every time I roll the die, if I roll a 4, I'm going to call that capital A, event A, meaning I rolled it and the 4 came up. Does that make sense to people? It's a way of doing this shorthand, so I don't have to write out all those words every time. So I might just say instead, all right, A is this event, the event that you roll the die and get a 4. And then I'll compute the probability of A. All right? Now, classical probability. A basic formula. Okay? Which your book, and actually, it's probably on your formula sheet from the exam. They don't even get it because it's so basic. They don't even give it. They say you're going to know this. The probability of an event occurring equals, and they're going to write little s over little n. Now, we've had little n before, interestingly enough. What was little n for us? It was kind of a total, right? It was a sample size. Remember that? Okay. Now, here, what it's going to mean, it's going to mean the size, of what is called the sample space. And this S is the size of the event. I'm not sure that these words help you yet, so I'm going to write one more definition that I think does help you. These words will be helpful soon, but right now I think this will make sense. When I write S over N, that's the probability of A, S here, this is the number of ways the event can occur whereas n is the number of ways something can occur. And then I have an important note to write. Does this English make sense to you? The number of ways something can occur? When I roll a 6-sided die, what's the number of ways something can occur? 6. So in that example, the probability of, I'll call it rolling a 4, the number of ways something can occur is 6. What's the number of ways the event can occur? Well, how many 4s are there on the die? 1, right? And so we say the probability of rolling a 4 is 1 out of 6. Is that okay? Now, important. I used a word here called ways, which is kind of weak. It's not very good mathematics. Unless I really stress this, and then I think we're okay. All ways must be equally likely this formula to hold. So that's very important. Is it just, remember, I said n is the number of ways something can occur. Or sometimes people will say the number of possibilities. How many possibilities are there when I roll a six-sided die? There's 6. Are each of the numbers equally likely to come up? Yeah. We actually saw that in the data that we showed. And but only one way you can actually get a 4. Okay? So as an example, suppose I roll 2 dice. Okay? Let's compute the probability that I roll a 7. Okay? Now, I'm going to do something incorrectly up here, and I want you to comment on it. Better do this in red or something so you know it's wrong. So this is incorrect. Well, I can roll any of these. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Isn't that correct so far? I could roll any of those. Now, how many of those numbers are there? So is the probability equal to, how many numbers are there here? 11. So is the probability 1 out of 11? And that's a big no. No. Okay, why? That's the big question. And can you talk about that with someone near you for a moment? What's wrong with my logic here? More than one way of rolling a 7. And actually, I remember talking to you guys about that, right? Matter of fact, what does that mean? If there's more than one way of rolling a 7, and let's compare it to, say, rolling a 2. What can you tell me about rolling a 7 or rolling a 2? Scott? Yeah. 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 And so why is it that the probability formula did not work? What's wrong with what I did? Yeah, David? Right. So there's more than one way of getting a 7. And there's another problem. These denominators, how'd I get 11? Well, I counted up all these different things that could happen. But these different things that could happen are not what? Let's look at that last slide. What's the important point? They're not ways that are equally likely. For example, what is one of the least likely things to happen when you roll 2 dice? To get a 2 or to get a 12. Would you agree that is less likely than rolling a 7? And we saw that because we had this kind of a distribution, a bell curve that we actually observed, right? We saw it was less likely. And now we can maybe understand why. So I actually want to compute the probability of rolling a 7 with you. In order to do that, I need to represent what's called the sample space. And I'm going to do that in the following way. I'm going to represent the sample space with ordered pairs, where one die I'll put before the comma and the other die I'll put after the comma. And I'm going to list every possible thing that could happen, right? Now the first die I roll a 1, let's say, right? Well, what could happen to the second die? Well, you could get a 2, or you could get a 3, or you could get a 4, right? Or you could get a 5, or you could get a 6, right? So that's what happens if you roll a 1 on the first die. And if you roll a 2 on the first die, well, again, there's 6 different possibilities as to what could happen on the second die. So let me ask you, if I were to list all the possible things that could happen when I roll 2 dice in this way, how many things would you actually list? Tyrone? 36, right? 6 times 6. I mean, eventually you would get all the way down to here, 6 comma 6, right? Oh no, 6 comma 1, 6 comma 2, 6 comma 3, 6 comma 4, 6 comma 5, 6 comma 6. Do you guys see there would be 36 possibilities here? It's a 6 by 6 square, right? So it turns out, if I were to compute this correctly, the probability of rolling a 7 is actually going to be something out of 36, because each of these possibilities is what? From the last page. Equally likely, right? Each of these possibilities is equally likely to occur. And now, you guys were talking about different ways you could get a 7. How many different ways could I get a 7? 6, somebody says, because why? Well, take a look right here. Is that a 7? 2 and a 5? What else could happen? Okay, or the other way around, right? A 4 and a 3, a 5 and a 2, and here's my 6 and 1, right? So there are 1, 2, 3, 4, 5, 6 different ways in the graph, in the grid here, to roll a 7. So the probability of rolling a 7 is 6 out of 36. Which I know to some of you guys simplified. And so you wrote it's 1 out of 6. So if you roll 2 dice, there's a 1 in 6 chance that you're going to roll a 7. Is that likely? Compared to what? Okay, let's compute that. What is the probability of rolling, how about a 3? Well, again, if I list them this way, I can see that the sample size would be 36. The probability of rolling a 3 would be 2 out of 36, which is 1 out of 18. Okay? And you know what you want to do is you want to do some calculator work with this. Yeah, I'm over time, and I apologize for that. That won't happen again on a test day. Okay? So I will stop. We finished class last time talking about this example where I rolled 2 dice and I want to compute the probability of rolling a 7. And we said it's not 1 in 11, even though there's 11 different numbers that might show up. And you guys seem to understand that when you roll 2 dice, there are more ways of getting a 7 than there are of getting a 3, right? And when you roll the dice, you'll express this as a fraction sometimes, or the other thing you guys might want to do, and I don't know if you did this for homework or not, pull that calculator out. If I get something like 1 out of 18, that's a fraction. I understand that. But sometimes it's more helpful to actually compute the decimal equivalent. So I'm just going to type in 1 divided by 18. Okay? Now what's that? Well, it's a decimal, right? So I could say it's 0.0555. Eventually they made one of these 5s a 6 because they're going to round. The 5's go on forever. But that's it as a decimal. What is that as a percent, by the way? That's about 5.5%, right? And again, when you do a decimal like this where you're rounding, it's approximate. But this is a little bit over 5%, your chances of rolling a 3. Is that okay? Whereas, what's your chances of rolling a 7? Well, 1 out of 6. Let's figure out how likely that is. Oops, wrong one. I did 1 divided by 3. See that? 1 divided by 6 is, it's actually 16, and if you want to write 0.67%, that's an approximation. If you write 16 2/3%, that's exact. I'm okay with this. One thing I'll tell you I don't want, if you get a probability of 1/3 for something, what does that equal? I just showed that by accident, but I'll bring it up since it came up. Right? That's the 3's repeating. What percent chance is that? 33.3%. As a decimal, 0.333, I'm okay with that. What I don't want you to do is just write down 0.3. Because if you just write down 0.3, which sometimes people do, what does that actually mean? 30%. What fraction is 0.3? That's 3/10, see? 30% is different than 33 1/3%. Okay, Kristen? Yeah, if you put the line over it, then I know what that means. Okay? But a lot of times, the general public might not. So you won't see 0.3 with a line over it very often. You might see people write 33 1/3% or 33.3%. They'll round. What I'm saying is don't round at that first digit or you're gonna be inaccurate. Sonia? Yeah, that'd be okay. 16.7% would be okay. Three significant. So that's the book's advice, by the way. Yeah, 3 significant figures. Is a good rule. Whereas if I just put 0.3, I'm only doing 1. Okay, David. Yes. Yes. Okay. Now. Good. I think I'm okay here. All right. I wanted to do one more example, like I said, and this will help to answer Craig's question. But before we do the example, this is one of the more important ideas we're going to cover in this course. And you've seen it at work already. It's called the law of large numbers. Okay. The law of large numbers. And when I say the law of large numbers, you might think of this as the law of large samples. Okay? And basically what it says is, as we increase our sample size, to make it very large, or to make it large, we find that the relative frequencies approach the proportions we get, or we compute, let's say, using classical probability. Kind of a long statement. I hope it's not too long to understand. Let me highlight what I'm saying here. As we increase our sample size to make it large, remember what letter we used for sample size? Little n. Remember that? Little n told you how many data points you have. You guys with me? If I make that really big, what should happen is relative frequencies will approach the proportions we compute using classical probability. Now, Craig asked me, what is this? How are these different? And I'm going to show you that in my example here. Jim? Okay, yeah, so I guess what I want to say is that's probably what they say. I don't want to say correct, but yeah, the more likely the classical probability means something, okay? You know, I have two dice here. I'm going to roll them. What do you think I'm going to roll? Can everyone write down what you think I'm going to roll? By the way, when you write down your number, as long as you're between 2 and 12, then I'll let you stay in the class. Okay? I'm going to roll 2 dice. Juliet has volunteered to be my independent, nonpartisan judge. All right? Let's write that. 4 and 5. Well, so she actually wrote down what she thinks each die is going to be. Instead of doing that, I guess what I should have said is write down what you think the sum of my dice is. Okay? So write down the sum. And again, it should be something between 2 and 12. You guys agree on that? Because we have between 1 and 6 on each die. Juliet's going to check it out. By the way, maybe we should see what people bet on first. Anyone volunteer a response? What do you think's going to happen? David? 7. How many put 7? What do you think I'm going to roll a 7? Really? Oh, you said no. What'd you put down? You put down 4. Is that a bad choice? Well, remember, we can compute what the probability is of these things happening. Matter of fact, we did, right? We computed, where was it? Here it was, 1 out of 6. This is the chances of me rolling a 7, a 16% chance. Does that mean I'll probably roll a 7 or probably not roll a 7? Probably not, but it's the most likely of all the possibilities. Does that make sense? Okay, let's see what happens. What I roll? Juliet? 7. Was it magic? No. Let's play again. Write down what you think I'm going to roll. Ready? What I get? 6. Anyone get both right? Wow. Now, if I had rolled a 2, that could happen, right? Very unlikely things do happen all the time around us. But they don't happen lots and lots and lots of times. If you saw me roll 20 snake eyes in a row, what might you suspect? Jim? I'm cheating somehow. Weighted dice. If you saw me roll that many snake eyes in a row, you'd say, well, understand it happening once or twice, but that, see, you have a notion of probability. You have a notion of the law of large numbers. That if we take a large number of samples, we shouldn't be getting that snake eyes all that often. Does that make sense? That's the law of large numbers. I moved away from the mic. I'm not sure how that'll record, but we'll save it, just in case. Mendel produced 100, hold on. No. Yeah, 152 yellow peas. And 428 green peas. I don't know if you know all the details of this experiment. It's very famous. But here's the remarkable thing, maybe, is these peas all came from the same set of parents. Okay? He had this pea plant and this pea plant, and he female, male parts, and he did everything himself. This is genetic engineering back in the early 1800s. Okay? So he knew the parents. By the way, do you know what color the parents were? Both parents were green. Okay? Both parents were green. There's a little more to the story. Each parent each of the parents' had one yellow parent and one green parent. Okay? So here's what he did. He was working on the idea of genes. And he had this idea that there's a yellow gene and a green gene. And his theory was that if you get both green genes, meaning your mom is green and your dad is green, you're going to be green. If you get both yellow genes, your mom is yellow, your dad is yellow, you're going to be yellow. What happens if you get one of each? Well, he had this idea that in either case, you'd be green, because the green somehow dominates the yellow. It's a darker color. This was his theory, and he wanted to prove it. So he did this experiment. He took his plants carefully. He knew who the parents were. He knew who the grandparents were, if you want to think of it that way. Okay? And what were his results? Well, in one sample, he was thrilled because he got 428 green peas and 152 yellow peas. By the way, in this example, what does n equal? 580. Okay. So now, I'm about to answer Craig's question. What is probability of being green? And we're going to compute this using relative frequencies. What's the probability of being green? Using relative frequencies. Now, what's that mean? It means, see, these things here, these are frequencies, right? 428 were green, 152 were yellow. But you guys tell me, how do I get relative frequencies? I take the 428 and divide by what? 580, because that's the size of the sample. You guys follow that? All right, let's do that. So we get the calculator out. 428. Yeah, some of you guys told me it's 73%. Almost 74, right? So let's say 73.8%. Okay? Is that okay? So here's the question. What does that say about his theory? See, according to his theory, he had the idea that each of these possibilities, 4 equally likely possibilities, he thought it's just like rolling 2 dice. The mom gives you either a green gene or a yellow gene, and the dad gives you either a green gene or a yellow gene. So it's just like I did with the dice. Green, 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 yellow, yellow, green, or yellow, yellow are going to be your genes. And you're going to be green. What's the probability of being green according to this classical probability model? Yeah, because it's 3 out of what? 3 out of 4, which is 75%. And what you're seeing here is you're seeing an example of the law of large numbers. Mendel had a large number of pea plants, right? 580. And that number, well, I don't know. Is that close to 75% or not? What do you think? How many say, yeah, that's close? How many say, no, it should be closer? So most of you said that's close. What if he had done the experiment and he had gotten 72%? You guys be okay with that? What if he had done the experiment and gotten 70%? Do you think his theory is still okay? It's just kind of what happened? What if he had done the experiment? These are rhetorical questions in some ways. I want you to think about these. What if he had done the experiment and gotten 51%? You might start to question his theory, right? He probably would have questioned his own theory. He'd say, the experiment isn't doing what I thought it would, so maybe my theory's wrong. Kind of like when I started rolling snake eyes 12 times in a row, you would question the theory that these are fair dice. You guys with me on that? So there is a point where you start to say, hey, wait a minute. Here's a tough question. At what point in this example should Mendel have started saying, hey, wait a minute. Let me ask you this. Would you expect Mendel to get exactly 75% of the peas green? Could it happen? Actually, I don't know if it could happen. Let's see. I'll tell you in a second. I guess it could. Uh-oh. What happened? See, if it had happened, what's 75% of times 580? Oops. If he had gotten 435 green peas, that would have been exactly 75. He didn't. Was he close enough? That's the subject of Chapter 5. Was he close enough? I want you to understand right now, that's not an easy question. How close do you have to be close enough? We'll get to that. For now, all I want you to understand is if you do a large sample size, you should approach whatever the classical probability says it is. Does that make sense? Okay. Back to Scott's question. Did I answer it? What was your question? Repeat it one more time.
When you were talking about the dice about law of 7.
Yeah.
16%. If you get more than 16%.
Oh, yes. That was the question. If I get more than 16%, is that okay? Well, it's kind of like this. What if Mendel had done his experiment and he got 437 green peas? That would be more than 75%, right? Is that still okay? He would have said, yeah, it's close. And when you do the law of large numbers, you don't expect to exactly get the probability, but you expect to be close if the numbers are large enough. Yes? Why? Absolutely. That standard deviation is coming back. It is not going away. When I said we're going to cover some important things in the first few chapters, you're absolutely right. That's coming back. David?
So for the rule of large numbers, it's all about flat numbers being close.
It's where the relative frequencies, what I underline up there, should get close to what you get if you compute using classical probability. And that's what I did down here. Okay? The law of large numbers, and I'll go back to it because I think I wrote it down. Yeah. The law of large numbers says that as we increase our sample size, the relative frequencies should, I said, get close to or approach what you would get if you compute using classical probability. That's here. Jim.